Alessandro Chiesa, and my supervisor, Simone Vitale. Good. So the VCG mechanism really deserves no introduction at this conference. It maximizes social welfare in single-good auctions, multi-unit auctions, and most generally, multi-good combinatorial auctions, which are now really at the frontier of auction theory. However, I wish to point out that the VCG is relying on the following implicit assumption. If I'm player I, I not only have the true valuation theta I star in my heart, I also happen to precisely know it in my head, because he has to bid it in the auction, right? If you think about it, this may not be so realistic because it's often very hard to know yourself. We therefore want to study the VCG mechanism under self-uncertainty. But how to model self-uncertainty? One possible way is to use maybe the Bayesian distribution. I knows the distribution from which his true valuation is drawn from. For instance, the distribution may be, say, the Gaussian distribution with the mean and standard deviation. But if you think a little more about it for a few minutes, that implies this player I can precisely compare the probabilities between any of his two valuations. So if you're willing to buy that the player does not maybe necessarily precisely know his valuation, how could he know so precise about the probability of his valuation being something? So this may also be too strong, and we wish to study a weaker model. That is the Knightian model. A player I, instead, knows a set of valuations, a set of distributions, from one of which his true valuation is drawn from. If there's only one single distribution, it boils down to the Bayesian setting. So of course, this is a weaker and safer model. As a simple example, the set could contain, for instance, all the distributions whose PDFs are between these two curves. Now the player doesn't need to precisely know the probabilities. So I actually have much more reasons to convince you that the Knightian model is a great one. For instance, there are practical reasons, there are examples in which the Knightian self-uncertainty really arise. And also, there are auction reasons. For risk-neutral players, which are the players that only care about their expected utilities, which are also the players I care about today, for them, in fact, Bayesian self-uncertainty does not yield any different player behavior. What I mean here is that he can just compute his expectation of the distribution and then think as if his true valuation is just that expectation. So this can be proved very mathematical formally, at least for auctions. Also, there are belief reasons. That is, Knightian self-uncertainty also allows us to capture the player's self-beliefs about his uncertainty. And perhaps the last but not the least, what I call the safety reason, I believe focusing on Bayesian self-uncertainty in all the contexts is like putting all the eggs in a single basket. It may not be so safe to do that. So at least for auction, I want to put this egg also in the Knightian basket. All right, so much for the motivation of the Knightian model. And one last thing about the Knightian model is that because I hope I have convinced you that one player can replace each of his distribution by the expectation. Therefore, the Knightian model is equivalent to say that the player knows a set of valuations, and one of which is just its true valuation. I'm going to call this set Ki the candidate set of player I. Okay, so for the rest of the talk, I'm not going to touch anything about Bayesian. So every Ki is just a set of valuations. Let's now go back to auctions. So in fact, with the same co-authors, we initiated this line of work in our previous paper and proved the following three theorems. Theorem 1. We showed that in a setting as simple as single good or multi-unit auction, dominant strategy mechanisms are useless. By useless, I mean they're really as bad as just randomly assigning the good to the players without even reading the input. This is really pretty bad, but I personally view this as a great opportunity. Because if our best friend, dominant strategy, is gone for this Knightian auction, that means we should start to build new tools and look at other solution concepts. Indeed, we immediately look at undominated strategies. That is to assume that the player will play a strategy that's not dominated. He may have multiple, but he's going to play one of them. In this case, again, in multi-unit auctions, with n players and m identical goods to sell, the VCG mechanism guarantees a social welfare larger than or equal to the maximum social welfare minus 2m delta. So m is the number of copies of the good, but what is delta here? So in order to introduce delta, let's just think about the performance of the mechanism. It has to sort of depend on the player's knowledge and accuracy on their evaluations. If they do not know nothing about the evaluation, then of course the mechanism cannot guarantee, for instance, any social welfare. We therefore introduce this notion in our prior work, that is the delta inaccurate setting. We see the setting is delta inaccurate if each player knows his valuation up to an additive amount, that's delta. For example, in a single good auction, it means that the maximum value in the candidate set minus the minimal value is at most delta. So now the yellow thing is basically a 3-player, 10 inaccurate single good auction setting. This can be similarly defined for multi-unit and combinatorial auctions. All right. So now with this notion of delta, I can formally state what its theorem 2 is about. So this is the only time in today's talk I'm going to formally state a theorem, because I really want to give you a sense that is how to estimate the performance of a mechanism even if players do not know their true valuations precisely. Which is, for all the delta inaccurate candidate sets of all the players, for all the strategies that are undominated, I'm using this UD to denote undominated strategies, and for all the possible valuations that are inside the set, inside the candidate set, the social welfare of the outcome of the VCG is larger than or equal to the maximal social welfare minus 2m delta. So this is the formal statement of theorem 2. And we showed also in our prior work that the V-creep or the VCG mechanism is in fact the best one among arbitrarily complex mechanisms. So therefore, theorem 1, 2, 3 together really shows the robustness of the VCG in multi-unit auctions. I view it as a very important extension to the very original paper of V-creep. Because even if the players have set theoretic uncertainties, still the V-creep or the VCG mechanism is the best one to choose in terms of social welfare maximization. So for today's talk, I want to go to a more challenging setting. That is, how about combinatorial auctions with n players and n goods? We prove two things. First, still for the VCG mechanism, the social welfare loss is in fact not that great. So the VCG has to suffer a social welfare loss that's 2 to the m, exponentially in terms of the number of goods times delta. But on the positive side, we show that if one is willing to replace undominated strategies by regret minimizing strategies, the social welfare guarantee starts to become good, which is only linear in terms of n and m. So I'm stating on the slides in terms of pure strategies, but in fact things also work for mixed strategies. They're much harder to state, so I'll skip it. So at this moment, we're facing two theorems. The same mechanism, the VCG, works great in regret minimizing strategies and bad in undominated strategies. So what is kind of going on? So what if I still believe that the players are utility maximizers? Are you really saying that the VCG is like doomed in this case? I will kind of answer this question at the end of the talk after building a bridging lemma between the two types of the players. So this is the agenda for the next like 4 or 5 minutes. So our first result here is about combinatorial auctions. Recall that if there are, in the combinatorial auction, there are m goods to sell, and each player's valuation is in fact a 2 to the m dimensional vector with one number for each different subset of the goods. And here we see the setting is delta inaccurate if the player's knowledge about each single coordinate here is an interval that has an at most delta span. Okay, this is the most natural definition you can imagine. So with this notion of delta inaccuracy, we proved the theorem. And in fact, the proof is very challenging, but today I only want to give you a sense about what is going wrong by illustrating a single Harding state. Think about a very simple player, player I. His candidate set to every single coordinate happens to be the same set. And this set has a delta span. I'm now going to use the red dot to represent an undominated strategy for him. Can he bid here? Here? Yes. In fact, he can even overbid. By how much? By something 2 to the n times delta. So, or more precisely, this arithmetic progressive sequence is in fact representing a strategy for him among many overbidding undominated strategies. So if you're willing to buy that this is one of the undominated strategies, immediately the conclusion of the theorem follows, because the social welfare has to be broken by this much. So I told actually a lot of friends of mine about this result. The first question I got is always, are you really saying that a rational player is going to beat that very awkward, like arithmetic progressive sequence? My answer is probably no. I'm not saying that. I'm only saying using utility maximization, which is about using undominated strategies, cannot rule it out. Therefore, let's look at regret. So in the regret world, actually things are very beautiful. For each player, reporting the midpoint is in fact a strategy with very low regret, regretting at most delta. On the other hand, for every single strategy with low regret, it is not going to be very overbidding or very underbidding. It may still go out of the interval, but it will stay essentially close to the interval. These two steps are again non-trivial to prove, but they together can just simply they together would simply imply the social welfare guarantee. So this is so much about the statements of theorem 4 and 5. So now let me make a promised detour to talk about something relating regret minimizers and utility maximizers. This is essentially the third result of our paper. Let's look at any game, not only just Knightian auction. There may be two types of players, utility maximizers or regret minimizers. If there's only one dominant strategy, then of course the set of UD, undominated strategies, and the set of RM, regret minimizing strategies, are both single. There's only one strategy to consider, and the players will be very happy. But what if there's no dominant strategy? Like in this Knightian case. The set UD and RM are unavoidably of multiple items. So which one does the player choose? The clock is ticking, and before the game ends, he has to pick a strategy. So one possible answer is maybe he will play a random strategy. But I want to say there's at least a second answer. For instance, for this utility maximizer, he may want to use regret to further refine his strategies. Pictorially, that is about a utility maximizer. Once he computes his set of UD, undominated strategies, pay attention that he cannot use utility reasoning anymore because UD of UD is UD. So what can he do now? Maybe it's not too bad for him to use regret to break ties and and further refine his set. So we call this the RMUD player. And similarly, one can define the UD-RM player. These two new types of players are a priori really independent. They may be very different from each other, and the two remaining sets may be even totally disjoint. But in fact, we should very surprisingly, the two players are the same. Not only that, the strategy, the remaining strategy set equals to something pretty simple, which is the intersection between UD and RM. Again, I want to say this is true for any game, not just the Knightian auction. So let's now apply it to Knightian auction. Remember our theorem 5 says that the social welfare guarantee is very good for regret minimizers. because RMUD is a subset of RM, therefore, it also implies that the desired social welfare guarantee works also for utility maximizers who only use regret to break ties. Okay? So this is really so much of the technical meat of today's talk, but I want to mention that I'm personally very interested in a very general agenda, that is how to handle self-uncertainty in mechanism design. Today, I'm picking this Knightian VCG option really as a special focus because I want to start with what we know the best. So tomorrow, I will encourage everyone sitting here interested in this talk to maybe go back and try to add self-uncertainty to the game that you're currently studying. Maybe we'll produce a new paper for it. I hope you will enjoy this talk. Thanks.
We have time for one last question.
So the agents don't know their own evaluations. That's an uncertain thing. But what about their information or knowledge or expectations, beliefs about what others are doing? Is that also uncertain? Or do they have some kind of equilibrium thinking going on?
So this is really a very excellent question. So first of all, we're adopting some setting that's almost similar to VCG. That is, the mechanism designer knows nothing about the players, and the players only do not have any beliefs or anything about other players, just like the classical VCG setting. So of course, one can start to introduce also beliefs or maybe even uncertain beliefs about a player, about others. So that would be definitely a more general setting, and it's a very interesting setting to study. So today, I'm not assuming anything like that. And why? Because this is the most general setting we can currently handle. And everyone here, including myself, is welcome to study the more general one, which will be probably more complicated.
Maybe we can take it offline because already we are out of time. Thanks. Thank you.